Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. In the last video, we defined continuity and learned how to check it using limits. We also saw that many limits can be evaluated simply by substitution. But why is that allowed? Today, we'll answer that question properly by looking at two key theorems that explain how limits behave when functions are combined or nested inside each other. Before we do that, let's warm up with two continuity problems. By the way, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. For our first warm-up exercise, we want to find the value of c such that our function f of x is continuous at x is equal to 1. Now recall the three criteria for continuity. The first one is that our function must be defined at a, or in other words, a is within the domain. So our a value here is 1. And we can see that it is in the domain because f of 1 is equal to c. Next, I'm going to combine the second and third condition. The second condition says that the limit has to exist at a. The third condition says that the limit as we approach our value of interest for our function must equal to the value of the function evaluated at a. So in other words, we want the limit as x approaches 1 for our function f of x to be equal to f of 1. But we know what the value of f of 1 is. This is equal to c. So in other words, we want the limit to be equal to c. Now the limit of our function f of x as x approaches 1 is equal to the limit as x approaches 1 of x to the power of 4 minus 1 over x cubed minus 1. And now we're going to factor both the top and the bottom. So this is going to be equal to the limit as x approaches 1. And the top can get factored into x plus 1, x minus 1, and x squared plus 1. The denominator here is a difference of cubes. So this gets factored into x minus 1 times x squared plus x plus 1. And now we can go ahead and cancel out the factor x minus 1 from the top and bottom. So we get this is equal to limit as x approaches 1 of x plus 1 times x squared plus 1 over x squared plus x plus 1. And now our denominator is no longer 0, so we can go ahead and use direct substitution. So this is equal to 4 over 3. So now if we take this and we go back to here, we said that in order for it to be continuous, our limit must equal to c. So then therefore, the value of c must be equal to 4 over 3. For our second warm-up example, it's something similar, but this time we have two values, a and b, that we wish to find in order for our function f of x here to be continuous on the interval -1 to 1. So looking at this piecewise function here, the only x value of concern is 0. And the reason is because this piece here is continuous on this defined interval. Because the only two values that cause problem here that would make the denominator 0 would be -1 and 0. But because we have rounded brackets for both, this interval does not include -1 and it does not include 0. Similarly for this piece over here, this piece is continuous on this interval because the only value of concern here is 0. But this piece, because of this rounded bracket, doesn't include 0. So because each piece is continuous on the interval that it's defined at, the only value that we're concerned about is the breakup point of this piecewise function, and that is at x is equal to 0. So here we can see that f of 0 is equal to 1. And in order for our function f of x to be continuous at x is equal to 0, we want the limit as x approaches 0 from the right side for our function to be equal to 1, and we want the limit as x approaches 0 from the left-hand side of our function to also be equal to 1. So let's do the right side limit first. The right side limit would be limit as x approaches 0 from the right-hand side. And the piece that we're going to be using is that top piece. So the expression is square root of 1 minus x minus 1 over a times x. We're going to multiply the top and bottom by the conjugate. So that'll be square root of 1 minus x plus 1 over square root of 1 minus x plus 1. Okay, so let's go ahead and simplify that. So this becomes the limit as x approaches 0 from the right-hand side. Now our numerator is going to be 1 minus x minus 1. And then our denominator is going to be a times x times the square root of 1 minus x plus 1. So now we can see that the top we have 1 minus 1, so that's just negative x. And we can cancel out an x from the top and the bottom, so we're left with the limit as x approaches 0 from the right-hand side of negative 1 over a times the square root of 1 minus x plus 1. And now our denominator is no longer 0, so we can go ahead and use our direct substitution. So then this is equal to negative 1 over 2a. And earlier we said that we wanted the limit as x approaches 0 from the right-hand side of our function to be equal to 1. So therefore, we want this value to be equal to 1. So now if we go ahead and isolate a, we get a is equal to negative 1 over 2. Next, we're going to do the same thing, but this time we're going to do it for the left side limit. So we get limit as x approaches 0 from the left-hand side of our function, and that is going to be b times x to the power of 4 plus bx over x squared plus x. We're going to factor both our top and our bottom. So then we get the top is b times x to the power of 3 plus 1. And then our denominator is going to be x times x plus 1. Now we can cancel out the x on the top and the bottom, so this becomes the limit as x approaches 0 from the left-hand side of b times x cubed plus 1 over x plus 1. And just like the right side limit, for this left side limit, we also want it to be equal to 1. So that means we're going to set this equal to 1. And we can see that now we're no longer dividing by 0. So then we get 1 is equal to, and then we're going to do our direct substitution. So this becomes b over 1. So therefore, the value of b is equal to 1. So the values of a and b that will make our function f of x continuous on the interval negative 1 to 1 would be a is equal to negative 1/2 and b is equal to 1. And now let's take a look at the two theorems relating to composite functions. The first theorem says that if the limit as x approaches a for a function g of x is equal to some value L, and f is continuous at L, then the limit as x approaches a of the composite function f of g of x is equal to f of the limit as x approaches a of just the inside function. But we know that the limit as x approaches a of g of x is equal to L, so therefore this is just equal to f of L. So essentially, all this is saying is that if the inside function approaches a particular value and the outside function behaves nicely at that value, then we can move the limit inside into the inside function. The second theorem says that if the function g is continuous at a and f is continuous at g of a, then the composite function f of g is also continuous at a. This theorem explains why complicated functions are still continuous. It saves us from having to reprove continuity for every new function that we encounter. So together, what these two theorems tell us is that limits pass through continuous functions. And that continuity survives composition. So in reality, we have already been using these two theorems without realizing it. So now that we know these two theorems, let's take a look at a couple of examples where we explicitly use these two theorems. So for our first example, we want to evaluate this limit. And we've done something like this before. This one, we can use our direct substitution rule. But really, what we're doing is our outside function here, f of x, is equal to the square root of x. And then our inside function, g of x, is equal to 5x squared minus 1. So the limit as x approaches 1 for our inside function, this is equal to 5 minus 1, which is 4. And our outside function here, square root of x, is continuous when x is equal to 4. So therefore, we can use the first theorem to say that this is the same as taking the square root of the limit as x approaches 1 of our inside function, which is 5x squared minus 1. And since we've evaluated the inside limit to be equal to 4, this is equal to the square root of 4, which is equal to 2. For our next example, let's take a look at what the outside and inside functions are. So here, our outside function f of x is equal to e to the power of x. And then our inside function g of x is equal to the square root of 1 minus x minus 1 over x. Now, f of x is a continuous function everywhere because e to the x is continuous everywhere. So that's why it doesn't matter what g of x is equal to, our outside function is going to be continuous there. So again, we can use that theorem to rewrite this as this is equal to e to the power of, and we're going to bring the limit in, so that'll be limit as x approaches 0 of our inside function here, which is square root of 1 minus x minus 1 over x. Now to evaluate that limit, we need to multiply it by the conjugate. So this is going to be limit as x approaches 0 of square root of 1 minus x minus 1 over x times square root of 1 minus x plus 1 over square root of 1 minus x plus 1. Now doing some simplification, this is going to give us our numerator is going to be 1 minus x minus 1. And then our denominator is going to be x times the square root of 1 minus x plus 1. The 1 gets canceled out, and then the x gets canceled out from the top and the bottom. So then we get this is e to the power of limit as x approaches 0 of negative 1 over the square root of 1 minus x plus 1. Substituting 0 in, and we get a final answer of e to the power of negative 1 over 2. And now let's do a recap of what we covered in this video. We learned that it's continuity that justifies substitution. If a function is continuous at a value, then limits can be evaluated by direct substitution. We also saw that for limits of composite function, if the inside function has a limit and the outside function is continuous at that limit, then the limit passes through. We learned that continuity survives composition, so that composing continuous functions produces a new function that is also continuous. And finally, before you start applying these theorems everywhere, make sure you always check the conditions first. These theorems only apply when the limits exist and continuity is guaranteed at the relevant point. And now, it is your turn to give this a try. Can you evaluate the limit shown on the screen here? Make sure to leave your answer in the comments below and let us know if you'd like to see more content on limits and continuity in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.